Hello world, this is Craig. I wanted to focus a little bit on the Monitor80 program, and I wanted a copy of this that I could have and completely assemble it start to finish, and also then be able to make changes to it or anything I wanted to do to modify it. The version that's available I got from Charles, and there's a text file. He did an OCR on this and then cleaned it up to make sure that everything was correct. But of course, you can't just pull this into the assembler. It's already been assembled. I've got the addresses on the left-hand side, and then I have the machine instructions, have the mnemonic, the arguments, and the comments. And my assembler just freak out if it saw all of these things because they just don't fit the requirements of the assembler. So I decided to go ahead and bring it into Excel to manipulate it to get it into a form that my assembler can at least get started on. I'm only going to hit the highlights on this. So I did a delimited file on the import. I only used tabs for the delimiters, and you can see down here how it's going to break this up. It kept the comments pretty much together, but it is dividing some of the arguments into two columns, and it is also putting the machine instruction and the mnemonic and occasionally one of the arguments in the same column. But that's as good as I'm going to get on this, so I went ahead and I did it that way. The next thing that I did was I made sure that everything was a text format for the column. The reason I did that was I didn't want it to strip off any of the leading zeros on my arguments, either if it's an address, a jump address, or if it's a port or a move immediate. I didn't want to strip off the leading zeros. So I imported it all as text format for the columns, and this is what I got. Using various functions, most things are fairly easy, and I decided that what I wanted to do, because I'm trying to make this in the end be exactly byte for byte the same as the original monitor, I want to make sure that all of the addresses are exactly the same. So you can see there are no labels in this at all. All of their jumps and their loads and their calls are all just to addresses. I took the first column, which is the octal address, and I changed those to make them a label. So to do that, what I have to do is I have to strip off the slash. I have to prefix that with a letter because my assembler requires that all the labels begin, they can't begin with a number, they have to begin with a letter. First column is done, so what were the addresses are now labels. They all begin with L, and then they have the actual label number, and they end with a colon. So my assembler will be able to accept that, and I'll have lots of labels. I've got 1,100 labels, but I'll go through, and when I get further down, the ones that obviously aren't being used, I'll delete them. But in the end, this will help me make sure that every time I assemble my code, it has the exact same address that it had before, and I'll modify these as I go along. The next column, you can see that it put the machine instruction and the mnemonic, and in some cases, the arguments in the same column. So that's easy enough to also separate out. I'm going to use a mid instruction and just get rid of the first 4 characters and save everything after that. So let me go ahead and do that. The next thing I'm going to do is my assembler requires all comments to begin with a semicolon. So I'm going to use the concatenate again and make sure that all of these comments, and the Excel spread these comments out into 2 or 3 or 4 of the columns here. So I'm going to take all of those columns and concatenate it with a semicolon to get a valid comment here. So let me go ahead and do that. That leads me down to the tricky bits. If we look at what the import did, it's interesting in that it created 2 columns for the numeric values. Some of these are move immediate values, some of them are output ports, some of them are RAM addresses, and some of them are jump instructions to other ROM or jump addresses to other ROMs. So what I'm going to do is create functions that do a couple of things. One is it's going to look at the value. Let me just look at the first column here. It's going to look at the value, and it seems that if it is in the first column and it's a 3-digit value, it's the second argument. So like the move immediate A, it has the value there. It's a 3-digit value, and it's the second argument. Where if it's in the second column, it is a port. So I'm going to write a little function that takes the value. If it's got 3 digits and it's in the first column, it's going to put a comma before it and a Q after it to make it the second argument. If it's in the second column, it's just going to put a Q after it to note to my assembler that it's octal, and then it's going to put it in the column right after the output instruction. So that'll take care of all of the 3-digit values. Going to write another function. If something is in this first column that has 6 digits and it begins with a 0, 1, for the most part that looks like it's a RAM address. So I'm going to do the same thing that I did with the Move Immediate with the 3-digit version. I'm going to put a comma before it and a Q after it. I'm going to write another function that if it is the same thing, 6 digits in the first column, and it begins with a 0, 0, that's a ROM jump, it looks like, for the most part. So those are all calls or jumps. If it begins with a 0, 0 and it's got 6 digits, I'm going to precede it with an L so that it matches the label. In the second column, if it is 6 digits and it begins with a 0, 0, that's the same thing. It looks like the jumps, looks like those are jumps or calls. So I'm going to do the same thing if it's in this column. If it's 6 digits, begins with 0, 0, I'm going to precede it with an L, put an L prefix on it, and move it over into that column. And if it begins with a 0, 1, let's see if there's anything in this column. Yeah, there's some in this column that begin with a 0, 1, like these STA instructions. If it begins with a 0, 1, I'm going to, that's a RAM location, move it over and follow it with a Q. The question is whether I should put a comma before it or not. Either way, it's not going to work for everything. Sometimes there's going to be mistakes. So let me write those 1, 2, 3, 4, 5, 6 little functions and let it operate on it and see where we go from there. Well, this is what I finally got to after doing the functions and playing around with it, and believe me, it wasn't exactly straightforward, but I got it. So I think I'm about 90% of the way there. I can, just glancing at it, you can see there's still some problems. Like here's a move MA, and so there's not a comma between there. And it looks like there's some, if things came from the second column and they started with a 0, 1, like these STA instructions, I didn't put a comma before it. So I'm going to have to come back, and if it's like this LXI H, there's going to have to be a comma before that. So there's some obvious mistakes in this still. But let me go ahead and export this and get it into my assembler and see how that goes. Again, that was far from being straightforward. Even when I was exporting it, Excel decided to put a bunch of double quotations in the file, but it was easy enough to go through and just do an overall replace, since I shouldn't have any double quotations in here, and get rid of all the double quotations. I did that, and this is where I am. I have all of my labels on the left-hand column with a semicolon, so the assembler is fine with all of those. All of the opcodes are okay. I then have the arguments, and the spacing is a little bit bad, but I can do as I go through this, I'll change those into tabs the way I like them, and all my comments are okay. So right now I still have, even after doing all this and bringing it in, I still have, the first time I brought it in, I had 1,000 errors, and that's when I found the quotation marks. I took that out, and that dropped it down to about 300 errors. And then I found where I had a bunch of places that I had missed the comma, like this move instruction between the arguments. So I went through and I did all of those, and now I have it down to, there's about 50 errors left in this. So now what I do is I am going through this code just bit by bit, going through the instructions and picking it out and finding exactly what all of this stuff is doing and getting my errors down so that I can do a complete assemble on this. And of course, as I said before, my main goal is to make sure that all of the addresses are the same so that this is byte for byte, exactly the same as the original code. So I'm going to go ahead and do some formatting on this, cleaning it up. I can name parts of the code so it's easier to find my way in this. Once I get to this point where it will almost assemble completely, I'm going to go through and put in any information that I can glean from the document or from the comments. So for example, right here, this says that it's an octal editor part of the routine. So I'm going to put in just a little place here and just put a note to myself. or to the future me, that this is the octal editor part. These are the editing routines. So any place that you see a jump like that, it's probably the start of something new. So if there's a jump or a reset, here's an indirect jump. So I know after that indirect jump, this is something different. And this is clear the breakpoint, clear breakpoint set. Now we have in the middle of this code these lookup tables. There's various lookup tables for the commands. And for right now, what I'm going to do is leave those the way they are. Eventually, I'm going to come back and recreate those lookup tables. But I do have to go through and change all of these to octal because my assembler otherwise presumes that they're decimal. So I do have to go through and change all of those to octal. So here I am. I've been putzing with this the last couple of days. And this is where I am. You can see that I have identified, as I said before, more things that I knew what they were. I could identify them. I also changed the labels to something that I could, read rather than just a address. But in some cases, like for example, here's the input byte to memory, so I renamed this as get byte. And then I have this kind of evolved. I've go through this and I overall evolve it. But you can see that I had a label here and I left all of the labels to begin with their original address afterwards. So I changed the L to an input byte as I recognized what this part of the function did, and I left the addresses there. And now I go through and I'm taking these addresses out. So here's, I just do a search, this input byte 1244, I'm going to call this like get byte 05 or something. And eventually get rid of all of the original octal addresses that are part of the labels, just because they make everything longer. Okay, so finally, with more puttering around with this, I got it so that it will assemble and it'll run on the machine, and I can run the commands, and as near as I can tell, everything is working as it should. There's a few things that I wanted to note to you that caught me, tripped me up for a little bit. One of them is that when this is connected to a teletype, what it does is when it receives a character in, it immediately echoes that on a bit-by-bit basis back out to the teletype. But when it does that, it complements the value to flip those bits. Since I'm using my RS-232 with my little adapter, I don't need to complement those bits. So I took out the complement and I replaced that with a no-op. And the reason I put the no-op back in there was to make sure that all of my addresses matched the original. I also completed the tables so that those are values that I create from scratch rather than just use the values that were in the original code. And you can look at the table in the instructions for the MOD80 supplement. They tell us that we have the 2, 3, and 4 letter tables, and then we have the argument and the command tables. So if it's a 2, 3, or 4 letter table, this is an ASCII value with the top 2 bits stripped off and then replaced with the control bit, with a pair of control bits. So for example, if it is a 3-letter opcode and the first character, so let's say it's a MOV instruction, the first letter is an M, they strip off the top 2 bits of that and they replace that with the 2 control bits. For the first letter, those 2 control bits are either going to be a 0, 1, 2, or 3. If there's no argument after this, it is a 0, and then a 1 means it's 1 argument with a destination, or 2 arguments, or 1 argument and a source. So depending on the first letter, those 2 control bits, it tells us what type of instruction this is. The second letter, so the O in our example, will have 2 control bits that are either no data byte, 1 data byte, or 2 data bytes. The third letter, the same thing, either it's a normal instruction, it's an exception to all the other rules, or it's a 4-letter instruction, or it's a 4-letter instruction and an exception to all the other rules. The 4th character is actually just thrown away. We really, as it turns out, we don't need the 4th character. We see if it's there or not. That tells us whether it's a 3-character or a 4-character, but we don't actually use the 4th character. If it, and here, these are the exception instructions, the DAD, the DCX, and the LDAX instructions. If it's in the command table, the first, second, and third letter are the ASCII values of the command, and then we have the least significant byte of the address and the most significant byte of the address, and that's the address where the command is located, where we're going to jump to. Okay, so that all said, this is what I did for the command for the tables. First thing I did was I created masks, a clearing mask that clears the top 2 bits, and then a set of masks that either, if it's the first letter, second letter, or third letter, and depending on what it is, I select the mask for that. If we look at the jump if carry instruction, for example, the J, the first letter, we're going to clear the top 2 bits, and we're going to OR that with the A0. So we're not going to set any of the command bits. It's just going to be 00 for the J. For the second letter, if we look at our instructions, the jump if carry has got 2 bytes that follow it, which is the address of where we're jumping to. And so we're going to take the C, we're going to AND it with the clear mask to get rid of the top 2 bits, and then we're going to OR that with B2 to set the top 2 bits to tell it that it's got 2 bytes for the instruction. And then this 332, that's the actual JC machine instruction for the jump if carry. So that's how we get all of the tables. So we have the masks, we then have the 4-letter tables. So here's a call, here's a push, here's the exchange, and so all of the 4-letter instructions, the 2-letter tables, the argument tables. So this is all of our registers, our stack pointer, our memory. So we have the B, we clear the top 2 bits, and then we OR that with A1 for the mask. We have the command table. These are all the commands that the monitor knows. So execute, locate the current pointer, dump the program in octal, and so forth. So all of our commands, and then all of our 3-letter opcodes. Okay, so right now these are tucked into the middle of the program, but the way I've assembled this, I can, when I don't want this program to be a exact duplicate, I can easily move that to the end of the program where it's more convenient. So another thing that tripped me up in a couple of places, they're very kind to give us in the manual the location, the memory locations, and the RAM that they use for all their scratch pad areas. And so you can see in some places they just use one value. In some places they double use a value, here where they have the AL store in 14 and 15, but they also use 14. They reuse that location for a flag occasionally. And if you're not real careful and you would just use location 15, for example, that can completely screw up the program. So I had to, a couple of places they really caught me with this, where I was a little bit too cavalier in just assigning the scratch pad area for it. And the other place that they do sometimes is they will use these as individual scratch pad areas. They use this in Little Endian, and so sometimes they wanted to just address the higher byte, and so they would do that individually. And so it was just a matter of overlooking things and not being careful enough when I was doing that. Okay, so basically I've got the program now where it runs. I think I have fixed all of the bugs in it. I'm going through, and anytime I get more time, I go through and I clean it up to get rid of any of the leftover octal addresses that are still part of the labels. And I see here I still got some formatting places that I have to take care of. Since you can have as many comments as you want and you can use equates and so forth to make the code more readable, I put all of that in. Have all of the RAM reservations that they use. They have a address pointer table that is in RAM that allows us to use each of the restarts. So I put those in. And then from here on out, while it looks a lot different, when it's assembled, it actually is byte for byte equivalent to the code. And the only exception is that one place where I had to change the complement accumulator value with a no-op to get it to not invert the teletype output bit. Okay, so that's a big step. I'm pretty happy with myself to get that all done and assembled and working. And so the good thing is that now I have this running on the machine and getting a feel for all the capabilities of this monitor. And some of the things, I'll do another video of the capabilities of the monitor, but it is really nice to have the be able to put in the mnemonics directly and have the disassembler in it. So I'll show you that in the next video, but if you have any questions on this, let me know. But until then, thanks for watching. Bye-bye.